Welcome to the complex analysis lecture number 6, and we are talking about singularities in the previous classes, and we are going through two singularities, that is isolated, non-isolated and poles. And now we are discussing about removable, which is also known as non-essential, and irremovable, which is known as essential singularities. So if we have a singular point at z equals to z naught such that for finite value of n we must have limit z tends to z naught, z minus z0 whole to the power n f of z exist or may be 0 for finite value of n. Then it is called removable or non-essential for finite value of n. Remember, for finite value of m, if these limits exist or may be 0, then it is called removable or non-essential. Let us take an example. Say f of z is equal to sin z by z. So limit z tends to 0, so z equals to 0, so z minus 0 into sin z by z. So this gives z cross out and this gives 0. So the limit is exist for finite value of n, so n is 1. So this is the removable or non-essential singularity. Okay. Now considering the next part, that is irremovable one. If the function is such that limit z minus z0 whole to the power n f of z exists or may be 0 for infinite value of n, then this gives the irremovable singularity or essential singularity. For example, you can consider f of z is such that 1 by e to the power z minus 2. So z is equal to 2 is a singular point which is irremovable, because this gives and series, that is f of z can be written as like this: 1 plus 1 by z minus 2 plus 1 by 2 factorial 1 by z minus 2 whole square plus 1 by 3 factorial 1 by z minus 2 whole cube plus dot dot dot. So it is for infinite value of n. So this function has irremovable singularity at z equals to 2. Okay. And the next singularity we are talking about is zeros of an analytic function. Zeros of an analytic function. Zeros of an analytic function. So if a function f of z is analytic at z is equal to z naught, then its neighborhood of z0, where the function can be expanded in Taylor series. We can easily say that if a function f of z is analytic at z equals to z0 inside a region, then it can be expanded in Taylor series like this. Okay. Here a0 is f of z0. Okay. So it is given like this. So let us take an example to understand the zeros of an analytic function better. So let us take an example such that f of z is equal to z minus 2 whole cube sin z. Okay. Now we can easily say that f of z0, that is z0 means to give the function 0. Okay, fine. Now let us find the first order derivative f prime z, and this gives f prime z at z minus at z0, f prime z at z0. So this will also give 0. Okay, and its second order derivative at z0 is also give z0 is 0, but for its third order derivative at z0 is equal to 2 point, it does not give the 0 value. It does not give the 0 value. So when its derivative does not give 0 value, then we have to count this order for the zeros. So here the function has zeros of order 3. Okay, zeros of order 3. Next, we are talking about branch points, singularities. So, number 5th is branch point. So, you can write the definition if you want. A point on the complex plane having the property that after comparison of a circle given function does not restore its initial value is called branch point. Hope you does not understand. So it is better to consider an example to understand this branch point better. So let us consider the function f of z equals to z to the power half. So in the Argyle diagram, this can be drawn like this. This is the imaginary part, imaginary axis, and this is the real axis. Okay. So we are taking two different points, that is z1 and z2. R1, it is R2, and it is theta, and this gives 2 pi minus theta. Okay, this gives 2 pi minus theta. Now we can write z equals to r e to the power I theta by 2. In the first class of complex analysis, we are talking about to take the complex function like this, r e to the power I theta. So it is given as half, so it is I theta by 2. Right? Now consider two different points z1 and z2 just above and below the real axis. Okay. So f of z1 gives the function r1, so let r e to the power I theta by 2, and the function f of z2 gives r e to the power I 2 pi minus theta by 2, that is r e to the power I pi into e to the power minus I theta by 2. Okay. Now if we put theta is equal to 0, that is in the real axis point, theta equals to 0 gives this in the real axis point, in the real axis. Okay. So if we put theta is equal to 0 in this gives this gives, here it is half is there, z to the power half, so it is half, right? So this gives r to the power half, but this function gives minus r to the power half. So the function does not exist on a particular point. So these points are called branches of points. So these are known as branch point. Okay, hope you are understanding the singularities and Taylor series and Lorentz series. And the later classes I am discussing about the residue theorem, or how to find the integration of a particular integration of different types, like from 0 to 2 pi or minus pi to pi, or any other kinds of integration, definite integration in the use by using residue theorem. And I am providing some problem sets if you are interested. So my email ID I am giving. You can further contact me on my email, that is billodol764282@gmail.com. If you have any suggestions or problem regarding these online classes, you can contact me on my email, that is billodol764282@gmail.com. Okay.